Okay, let's go through an example of seeing the connection between the reflection coefficient and the impedance and how it turns out to be in the Smith chart. This particular example, we are having a transmission line of characteristic impedance 50 ohms, which is going to be typically the case, is being terminated by a set of five different load impedances. We need to find the reflection coefficient for each case and then indicate them in the complex plane and in the Smith chart. We know how to do that analytically. We will see that how these different load impedances map to in the Smith chart. To do this analytically, we got this equation, which is relating the load impedance to the reflection coefficient as ZL minus Z0 over ZL plus Z0. So for these five different set of impedances, all that remains is to simply substitute the load impedance to the corresponding given value. So the five load impedances that we have been given is ZL equal to 0, which represents a short circuit, ZL equal to infinity, that represents an open circuit, ZL equal to 50 ohms. Since the feed line is also 50 ohms, this load impedance is matched to 50 ohms. Then we have the fourth one is a ZL having 16.67 ohms as the resistance and a reactance of minus 16.67. The minus means it's going to be a capacitive load. The ZL of 50 plus J150 is an inductive load. If we do the analytical calculation based on this equation, for that given load impedance, we can find the reflection coefficient and we obtain the values of minus 1 for a short circuit, plus 1 for an open circuit, 0, a reflection coefficient of 0 for a matched circuit, which should be the case, a gamma L of 0.54 and an angle of 221 degrees for the capacitive load that was given, and a magnitude of 0.83 and an angle of 34 degrees for an inductive load that was given. So let's plot it out in the complex reflection coefficient plane before we go and plot it out in the Smith chart. So these five load impedance values, the reflection coefficient that we obtain out of it is being plotted here in the complex plane. A corresponds to a short circuit having a reflection coefficient of minus 1. So in the complex plane, that maps to this particular point, which is minus 1. Remember, the center of the complex plane is gamma equal to 0. The left half is minus 1. Minus 1 meaning the magnitude is 1 and the phase is 180 degree, which represents a short circuit. An open circuit, which is the load B, maps to plus 1, which is this point over here. A magnitude of plus 1 and a phase of 0. The third impedance that is given is 50 ohms, the matched load, which is offering a reflection coefficient of 0, which means we are right at the center of the complex gamma plane. The point D, the reflection coefficient for the load D is having 0.54 as the magnitude and the phase is 221. The phase, remember, is always from the x-axis, is measured from the x-axis, and that point maps to this particular point in the complex reflection coefficient plane. This particular angle is going to be 221 degrees. How about the inductive load? The radius is 0.83, slightly larger than the capacitive load that we had. The capacitive load had a radius of 0.54, whereas the inductive load has a radius of 0.83, which is more than that of the capacitive load. And its phase is 34 degrees. So from the x-axis again, you are moving by 34 degrees to identify that particular point. So this is how the five impedances that are given looks in the complex reflection coefficient plane. How about how they look in the Smith chart? As we said, a Smith chart is essentially viewing the reflection coefficient in the complex plane, all the 5 points map exactly to the same corresponding points physically in the Smith chart as well. Each of those 5 points map exactly physically to those locations. However, in the Smith chart, we can directly read the resistance and the reactance offered for each of those load impedances.